Okay, so a dynamics workshop given by the CCPN team, and you'll be using some data from that recorded by Fred Muscat, which is our facility manager on GB1. Let me start off by thanking everybody, because otherwise I'm probably going to forget that. So you have here the CCPN team. So Gary's online, Vicky's online, Elisa's online, there's myself, Ed is online, and Luca's online. Morgan Hayward, my PhD student, was not in this picture yet. As you can see, I draw upon some past data. Hugo is online. Marco, some figures, some people, some materials from the EMBO courses in which I teach. It just was nice to use some of the figures and things. So what I'm going to tell in this first 30 minutes is the first 2 points, basics of relaxation, and sort of how can we apply and do something with that one before we go to the practical session later on. Now, just a take-home message for you all, if you're not familiar with this one, or not. So relaxation is the return to equilibrium of our NMR magnetization. Relaxation typically results in the exponential decay of our measured signals, and it gives us per atom or per residue rates for those decays. The relaxation is caused by random overall motions of the molecule and the local random fluctuations within the molecule. And as such, we can interpret those relaxation rates to give us information about the molecule. That is size, shape, aggregation, and it can give us information about individual atoms and residues. For example, the mobility, are they subject to chemical exchange, conformational changes, and all of those items. And that's why we're interested in doing these kind of experiments. Now, you probably have seen at some form or another this particular figure, which gives you here on the top sort of the mechanisms at play in biomolecules, all the way from vibrations, which are not so interesting, but then some sort of more local motions, rotations, some side chains that move about, all the way up to much slower processes which deal with like folding and allostery and catalysis and ligand binding. And you see this scale is a logarithmic scale, so it covers a very wide range of time scales for all these processes. And we're fortunate in NMR, indicated by the red lines here, approximately, of course, that we have all these parameters that can tell us something about these processes. And by measuring all these rates and all these effects, we can actually learn something about our biomolecule. So today we are only going to focusing on these 3 rates, R1, R2, and NOE for the N15. But it's not limited to that. And like I said, the setup that we have will be very similar for doing other things later on, for example, with CEST or CPMG relaxation dispersion, any one of those other types of experiments. Okay, so just a quick recap. If we have given a pulse and we detect our signal, then we measure something like this, and typically we measure a complex signal, so we have something that goes with a cosine and a sine, and that comes into our detector. But we also know that that signal disappears. In this particular case, we just phenomenologically add a term there, which is a decaying time constant to the signal. Now, what we do with our signal, we apply a Fourier transform, and we get the real signal, the in-phase signal, and the imaginary signal, which is the dispersion signal. But already from the real signal, we can see that that involves T2. Or in other words, if we look at our line here and the width of that line, it is the width of that line, either in frequency or radians, is proportional to 1 over T2. Or it is proportional to the R2. So line width and relaxation intimately are linked together. And hold that thought, because I'm going to come back to that one later. Now, the signal that we measure, like I said, is an exponential decay. So we typically write something like this, that we have some kind of magnetization which decays with some time constant. We call this T2 for the transverse relaxation time, for those things which are in the XY plane. And we either can talk about rates, that's what I prefer to do, or transfer relaxation time, which is essentially the inverse of the rate. Similarly, for the longitudinal magnetization, which we have disturbed from its equilibrium mz position. So it will go back with an exponential time constant like that. So that equation looks slightly more difficult if you write it like this. Here's the exponential part of the equation, but it's much easier to think of this as a disturbance of the Z magnetization, and that will just go back to its zero time point magnetization, again with a corrected time called T1, which we call the longitudinal relaxation time, or a rate R1, which is the inverse of this T1. So the equation for R1 and R2 in that particular case are very similar. They're identical, they're just exponential. Just as a reminder, the experiments that we're going to be using are all derived from our HSQC, which of course is a two-dimensional experiment with the nitrogen along the F1 axis and the protons, the amide protons along the F2 axis over here. And what we are going to be doing for our experiments is just tag another time period, typically in front of this sequence. And this time period is actually a pseudo dimension. So our experiments that we get are also pseudo 3Ds, as we call them, or just a series of planes, 2D planes. And that's how we typically deal with them. So you have the plane in this way, and then there's just a stack of these different planes, which all are dependent on some parameter t, which is essentially the parameter that we have changed in our measurements. So just to give you an example, so here's the same figure again, t here, and here is the decay that we then measure of such a signal. And actually this comes straight from the tutorial manual. And it doesn't make any difference whether we are looking at R1s or R2s, because the shapes, those are just exponential decay curves that we're interested in examining. Okay, as a result of doing that for each of our residues, we get essentially sort of a bar plot. So what we typically get at the end are residues over here. So it's just residue number and those rates plotted here for R1 and here for R2 on Hugo's favorite protein path. And that is because we can do this for every single peak of the 2D HSQC and just measure the rates for that particular point. Now, the question I really would like to pose here is, what is causing this relaxation and what can we actually learn from it? Now, going back to what we all know, in NMR, we deal with spins, and we typically have fewer spins in the beta state compared to the alpha state, just schematically indicated here. And that's the, let's call the Z magnetization equilibrium. Of course, it's dependent on the gamma, but just with a positive gamma. Now, what we do in our NMR experiment, we give a pulse, and essentially we flipped some of the spins from the one state to the other state, indicated here by the gray arrows that turn around. So relaxation, one would assume, also has to involve something that flips the spins back. In this particular case, we talk about T1 relaxation, which essentially means the Z magnetization goes back to its equilibrium. So we have the same number of spins again in the alpha state compared to the beta state as we started out with. So the process of relaxation will involve the transfer of frequencies that match the transitions that we have in our system. Now, where do these interactions that lead to relaxation come from? There's three that I'm going to briefly mention and discuss here. The first one is what is called the dipolar interaction, which is a through space interaction. If we have one spin called I here, another spin called S here, so think about this, for example, as the nitrogen spin and the proton spin of its direct attached protons, the two spins have an interaction. And why is that? Because they are small little magnetic dipoles, and magnetic dipoles have interactions with each other. So as soon as there's two of them, they start sensing each other. And classically, you can indicate that in this following plot. So here's the I spin. It's like a little magnet, so it makes these magnetic field lines essentially coming to the S spin over here. And classically, that is well described how this magnetic field lines will look like. And this is equation over here. Now, in quantum mechanics, we have a recipe for translating a classical interaction into what is called a Hamiltonian. So what you see over here is what is called the dipolar Hamiltonian. It looks a little bit rough, and don't worry about it. You don't even need to know that what it is, except that I'm going to talk you through what it actually will do in the end. Now, what we know from this Hamiltonian, from these little magnets in solution, is that the I and the spin will move about. They will tumble, the molecule will tumble, they may move relative to each other. So we have all these different orientation in a solution, which means that in solution, this effect from the dipolar interaction averages to 0. Now, although it does average to 0, it does cause relaxation, and well, fortunately or unfortunately. Now, this dipolar interaction you've seen before, and the fact that it doesn't average in solids, you may know, because in solids we do something which is called magic angle spinning. And that's effectively inducing the same effect, namely an averaging over all the orientations, so the effect goes to 0. We also may have encountered this effect as the so-called NOE, the nuclear overhousing effect, which gives you in your 2D NOESY spectra, which is also caused by the dipolar interaction of the two spins. And you may recognize these constants here from the original equation that is over on the previous slide. You also may know this as residual dipolar couplings, because what we do then is, well, we're not going to average the interaction completely, but we're going to make sure that there is a little bit left, like 0.1% or even less, or something like that. So the second effect that causes relaxation is the so-called chemical shift anisotropy. And what is that? Well, we all know that the electrons of the nuclei that we study cause the effective field to be slightly different from the magnetic field that we have applied. So B0 is the magnetic field that we have in our magnet, and it's shielded by this shielding constant sigma over here, giving us an effective field, giving us an effective frequency. And that's fortunate that it is, otherwise there would be very little to measure in biological animals. And then we work with our delta scale, which is just a relative scale in ppm that you're all very familiar with, presumably. Now, and here's just a proton example of a spectrum causing that with the different chemical shifts. Now, as it turns out, the chemical shift shielding is typically not isotropic. And what does that mean? That means that it has different value if you look in different directions. So the isotropic one that we see is actually the average of the magnitude across 3 different axes called XX, YY, and ZZ. That is, if you work in what is called a principal axis system. That doesn't matter. In physics, you can always go to another axis system to make things more simple, if that's convenient. But this equation, or this formula, essentially tells you if you look in a certain direction, it is different than when you look in another direction. And now you can see that if a molecule moves, that things will be different depending on how the molecule moves. So this effect is called chemical shift anisotropy. So anisotropy is just a fancy word that things are different in different directions. And for our isotropic shifts that we measure, we don't have any effect of it, but it does cause relaxation. Now, in most formulas, and the formulas that I will put up, it is actually the difference between what is called the parallel and the perpendicular components of the chemical shift anisotropy tensor, which essentially means we are going to assume that the YY and ZZ are roughly the same size. So there is one predominant direction and one other direction. Okay. Now, the third effect that affects our lines and causing relaxation is what we call chemical exchange. Maybe you've seen this figure many times over, that if a nucleus changes its chemical environment because of chemical exchange, its lines can adopt any one of those examples which are given here, and in one of those situations, either be in what is called slow exchange, so we see two lines, all the way to fast exchange, where we see the average of the line between the different states. The net effect is that this causes additional terms contributing to the so-called R2, so the transverse relaxation. You may have seen as actually that's being used in the CEST experiments, or relaxation dispersion experiment, where we particularly are focusing and studying these kind of effects. Now, just to pound in, here are the equations, and they look maybe a bit daunting for you if you've never looked at them, but let me sort of talk you through it and saying what they are. So here is R1, R2, and what we call the NOE type rate. And you can see here in this equation over here how the NOE that we measure is related to that rate. Now, I said there's three mechanisms, so we would expect to see the three mechanisms, and indeed that's the case. So what we see here in the green boxes are those things which result from the dipolar interactions. And you can see they all have the same constant. This is this d squared, which is the same thing that we saw for the NOE, which I put on the board, and for the Hamiltonian. So that's where it's from. Those are just constants. Well, the r is the distance between the nuclei, but for all practical purposes, that is a constant as well. Then we have parts which originate from the chemical shift anisotropy, which is shown over here in the blue. And they go with this constant c squared, where you see this chemical shift anisotropy term comes in. And then, of course, there's the exchange term, which is added a little bit ad hoc because it doesn't directly form Hamiltonians and a formal treatment, but it adds to the R2 rate. So we have these three terms contributing to these three rates, and the thing we're actually going to be measuring is this R1, this R2, and this one, the heteronuclear NOE, but I already told you that is essentially related to this third rate, what we have over here. So that's our job. Now, what I haven't told you is what are these things in between here, and they're called these so-called spectral density. So this stuff over here in these boxes. Now, if you look at that, those terms, there's 5 frequencies that show up that are important. Now, those 5 frequencies, to explain all of that, I would have other slides, or you would have to go through a lot of previous MBO material. But just to make this sort of understandable, well, it contains the frequencies of the nitrogen and the proton. And that sort of makes sense because those are the 2 spins that we're doing. It also contains the frequencies of the differences of those frequencies. Well, that originates from what are called zero quantum and double quantum terms. And those transitions are induced by the dipolar Hamiltonian. And then we have the zero frequency term, for which you have to invoke sort of adiabatic arguments or not arguments. But the thing is that we have 5 frequencies that apparently are important. But what is this spectral density? Okay, it's at this 5 frequency, but what is actually a spectral density? Now, for that, we are going to go back to a few slides. Well, first of all, we know, of course, that the frequency that we detect is essentially the gamma and B naught. So that's our frequency. Now, we know that that comes from a Hamiltonian. So the Hamiltonian is related to this gamma B field. So you can read the Hamiltonian as the energy, which you can read as the field. Now, we knew that the Hamiltonian had this constant one, this Zeeman term, which is dictated by the spin systems, but also this local part, which was the fact that we had these 2 spins that vary over time. So it's local because it's different, but also it's not constant because it's varying over time. And schematically, you could sort of say, okay, the magnitude of this h of t varies over time. It's just a random stochastic function. That indicates how the molecule moves effectively. That's a result of how the molecule moves. Now, we already know that the effect of this Hamiltonian over time, so we've integrated over time, that's 0. That's effectively saying, well, in solution, this was all averaging out to 0. So we didn't see any of this dipolar interaction. But what about the effect sort of squared? Because as it turns out, to do the relaxation analysis, you take what is called the double commutators. So let's not go there, but effectively you have to look at the effect squared. And it's clear that if you start squaring that it would not be zero anymore. So if we would take a look at this, the local t times the local t, and then integrate it over time, we would not get zero. Now, what I'm going to do now is introduce what is called a correlation function. It essentially says, okay, if I have a certain effect at a time t and an effect at a time some period tau later, and I multiply the two and then integrate, that is what is called a correlation function. It tells you how much whatever you have is correlated at time t and then some time tau later. Now you can imagine that if something moves very slowly, the position or the orientation of the molecule is varying very slowly. So you have a correlation between the initial position and the later position for a much longer time than when you have a small molecule which moves fast. To make an analogy, what you see here is the stock price for Coca-Cola and the stock price for Procter & Gamble. And you see that in 1990, those two were very, very similar. So the correlation of the stock prices of the two will be multiplying this one, the red one, with the black one, and then integrating over this period. And that would yield a positive value. But if I would correlate the stock price from Coca-Cola with the stock price of Procter & Gamble 1 year later, they may not correlate so well. And actually, if you do this exercise, then you see that the correlation falls off considerably because there's, of course, not very much a reason why the stock price will be correlated a year later. So this is a correlation function for stock prices. And we can essentially do the same thing for molecules, except that we don't know how molecules actually move or what their stock price is over time. So what do the physical chemists do? If they don't know anything, they assume a random Gaussian process, because random is always good. And then if we make it Gaussian, that means that certain rules apply. And as it turns out, for a random Gaussian process, the correlation function is an exponential decaying function. So if we assume that the molecule is just having that behavior, we can assume that the correlation function is an exponential. Now, the spectral density function is simply the Fourier transform of this function. And as we know, if we go from time, we do a Fourier transform, we go to frequency in the other domain. So this is what, because this is an exponent, this becomes a Lorentzian function, which has this shape, tau c divided by 1 times omega tau c squared. Omega squared tau c. So we call this the spectral density function. And these are the spectral density functions that we are going to be using. Now, what the next plot shows you that, of course, when you have a molecule that moves slowly, so it has a long correlation time, let's say 10 nanoseconds, then the correlation is very extends much longer than when you have a smaller molecule, which correlates at only, let's say, 2 nanoseconds. So this correlation time, the decay of this correlation function, tells you something on how fast the molecule is moving. Okay, now what about multiple processes? Because we already said, I mean, a molecule will probably not be determined by one process at all. Now, fortunately, sort of 30 years ago, two guys, now Lipari and Mr. Szabo, came up with a formalism which is now very well known, and they called this, that's now known as the Lipari-Szabo mechanism, which essentially said, okay, we are going to look at two processes, and we're going to assume that the two processes are independent of each other. And if that's the case, then we know that we can essentially just add the correlation functions. And if we're also going to assume that the time scale of those two processes is sufficiently different, and think about factor of 10. So for example, if the 1 is occurring on the nanosecond timescale, then the other one should be sort of a tenth of nanosecond of hundreds of picoseconds timescale, because that pretty much guarantees that they're independent. We're going to introduce something which is called a order parameter, which just is the weighing between those two terms. Now you have to essentially interpret as the first term of this correlation function as the overall motion, how does the molecule tumble as a whole, and the second term as the local motion, how does it behave on a local scale. Now, as we need to do the same recipe, we can just do a Fourier transform of that one. So that this is the Fourier transform, which gives us the sum of two Lorentzians. And then if we indeed assume that the one time scale is much smaller than the other one, we can just reduce this to two independent terms, which are just added with their s squared or 1 minus s squared values. Now, that turns out to be a very powerful mechanism to analyze our data, because we know that the molecule just tumbles. There's one tumbling, which generally assumes, and that means that all the other effects are going to be taking part for this other term here, which tells us a little bit about the local motion, and that's the things that we're interested in. Now, let's go to some areas of application where we can do with it. What about NMR line width? Okay. That's something that we like to know. So we already derived that the line width in frequency or radians is proportional to R2. Now, we also know that R2 was this long equation which had this term J0 in here. And if we take a look, for example, for a 10 nanosecond protein, this J0 term in this turns out to be the most important one. So we would expect to R2 to be proportional to J0. But J0 comes from this equation here, and which shows if we put 0 in here, we have that J0 is proportional to tau c. And there's also something which is called the Einstein's diffusion constant, which tells us, which is listed over here, which tells us that the tau c is proportional to the inverse of the diffusion constant. And we fill in a little bit. It turns out that tau c is proportional to the molecular weight. So we would expect that our line width proportional to R2, proportional to J0, proportional to tau c, proportional to the molecular weight. And does that work? Yes, that works like a very much indeed. So here you see a 4 nanosecond, 8 kilodalton protein, nice sharp line. We double the size. It's an 8 nanosecond correlation time, 16 kilodalton protein. The lines, you can already see they're broader. We go to 12 nanosecond, 24 kilodalton, even broader, 25, another doubling, 50 kilodalton protein. You see they have gotten broader and broader and broader. So it seems that there's some merit to what we're doing. And of course, when you have your protein, you'd like to, or your biomolecule in general, you'd like to have some idea what to expect and some idea what lines you can actually measure. Now, in 1994, a guy named Fuchsman published a paper where he essentially said, oh, if you take the ratio of the R2 and the R1, and this is the equation, but you can rewrite it over here, that's proportional to tau c squared. So if we have our rates, we can plot the R2 over the R1, and you see all the different values here. Well, this was less uniform, yes. This thesis is there, but if you take sort of the average of that one and you calculate then from this R2 over 1, the tau c should be around 9.7 nanoseconds. So a very easy check whether some of this makes sense. The heteronuclear NOE turns out to be a good indicator from what is the folded part of your protein. Again, here is the heteronuclear NOE plotted. And you see quite a bit of tail. You can plot this on this little structure, on the structure over here, and you get an immediate idea what is the folded part of the molecule. Now, another paper, and I think this is a little bit an overlooked paper, and we liked it in 2002, but it's quite Neller et al. Said, well, what about S squared? What about this other factor that comes into this equation? And they derived that if you multiply R1 and R2, it should be proportional to S squared squared. So again, here is a plot directly taken from the paper. You look at the average value, and that's, I would say, well, there's an average value of S squared of about 0.9 here for this particular molecule. Now, you can also use S squared very well to establish which ones of part of your molecule are a domain. So here again, plotting the order parameter derived from R2 over R2 times R1 as function of protein sequence, you immediately see that you have two folded regions over here with a linker and some termini over there. So that's the linker and some tails. Now, a third thing that you could do, you could take all your values and then plug it and essentially solve this equation and get something for S squared, the tau C effective, and the exchange contributions. That's called the Lipari-Vossoboff model-free approach with an isotropic routine, isotropic model. As it turns out, this is extremely dangerous. And the reason is that in an isotropic model, we assume that the molecule is spherical, that it doesn't have a preferential orientation for diffusion, for rotational diffusion. And in practice, there's almost not a single protein that actually is sufficiently isotropic to do that. So most of the times you have to do a model in which you include, which includes anisotropic diffusion, which essentially means that there could be a long axis and a short axis, something like this. So a non-spherical rotational diffusion. What does that do to the equations? Well, we need to adjust this part. It just gets slightly more complicated, and there's three constants, and there's some diffusion parameters. So there's a few more parameters that you need to fit. But the ultimate equation looks very, very similar, except that the overall motion now is this sum over these three orientations over here. But we still have the local term here with n minus s squared. So it's a more complicated model with a few more parameters to fit, but not fundamentally different because it's still an overall motion and a local motion type idea. One of the programs that you can actually do this with is, for example, with Model 3, but it's not the only program that is there. Going back to the same paper from Neller et al., one of the plots that are also very good to do is actually a plot where we plot the R2 over R1, so this Fuchsman estimate, which gives you essentially tau C, versus this R1 times R2, which is the S squared estimate. And if this molecule were isotropic at 80 kilodaltons, the points that we would like to measure would be somewhere in this region over here. And as you can see, this is clearly not the case in this particular case. So something else is going on, either chemical exchange or strongly anisotropic diffusion or so. So, but immediately already by plotting that, you get a pretty good idea that this is certainly not an isotropic system, and we need to be careful in what we do. Now, another way of looking at our data is what is called spectral density mapping. And here's our spectral density function. And I told you that 5 frequency are important. So we have those 5 frequency plotted over here. But unfortunately, we only have 3 rates that we measure. So we have 5 unknowns, 5 frequency, but only 3 rates. As it turns out, you can approximate these 3 rates pretty much by taking sort of an average at 0.87 of the proton frequency. And then we can reduce our equations with 3 rates to one with only 3 rates like this. And then becomes a linear problem. We have 3 things that we measure, 3 things that we want to know. That's a simple matrix type inversion that you can do. So this is the inversion, these are the rates we measure, and out we get our 3 spectral density function values. And what you can then do then is sort of make plots of all of them. So here are the 3 input rates, here are the 3 output rates, and then we can analyze where they are. As it turns out, there's a few plots that are quite useful. For example, the J0 versus the J omega H plot, which is over here. And for Hugo's protein, he could identify 3 quite distinct regions indicated here in the color coding that show you that those residues behave quite differently. The other plot, which turns out to be quite useful, is the J0 versus the J omega n plot, which you see over here. And the dotted lines are the lines for an isotropic rotating molecule. So these plots will also be generated at the end of the analysis, all automatically for you. Okay, going back to my initial slide, here are all the processes that we're interested in. Here are all the things that we can measure in NMR. Today, we're going to be doing only these 3 rates, but there's, of course, plenty more. I already mentioned Model 3 as a program, Relax. There's a Relax GUI, which I've not tried, but today, of course, we're going to use our own analysis assigned for that one. And at the end of this exercise, you essentially are going to be able to generate these plots, which I just showed you and alluded to you how we think that they are also very useful. I mentioned that we're working on the CEST and the relaxation dispersion for metals, and they're coming soon as well in the same setup. Now, one thing which I would really want to stress, so here's the output for essentially a table with all your results. I believe that is quite important to submit your results or eventually to something like the BMIB. So we are working now with, we are designing a way that you can automatically generate what is now called NMR exchange format files, which will allow you to deposit those data with the BMIB seamlessly, but must also hopefully integrate with other software packages on an automated session. So now I'm going to hand over to Vicky to start you the tutorial, the practical.
So we're going to start off with importing all of our data. So we obviously provided this dynamics tutorial. You may want to work with your own data, that's fine. We're going to start using this GB1 assigned.ccpn project. I'm simply going to take that folder and drag it here into the program, and it'll open. And it's basically, it's a very simple project. It simply has an HSQC spectrum of GB1 and which is assigned. So I should say at this point, thank you very much to Fred Muscat, who's provided all this data for us. Okay, now in this spectra section, that's where we've got all of our spectra, T1 data, T2 data, and the heteronuclear NOE data. You can see inside here, this is just a collection of UCSF data. Obviously, you could use Brooker data if you wanted, or whatever other format you have your spectra in. It's easiest in this case, simply we can just drag the whole folder in, and then it asks me, are you sure you want to load 10 items? Yes, I do. And you can see here, it's now loaded all of those 10 spectra. I can do the same for the T2 data. And the same for the heteronuclear NOE. So just note, previously I dragged things onto the sidebar, and you can see them here. If I actually drag them onto the spectrum, then the spectra will open automatically here in the spectrum display. But again, I can see them here on the sidebar as well. So that's the way you would probably want to do it. Then we need to tell the program basically that all of these spectra, we need to group them and say this is all of our T1 data, and we need to tell the program obviously what our delay times are. So I'm just here with the mouse and with the shift key, selecting all of these T1 spectra, and then right-clicking and going to make spectrum group from selected. And so I can now give my group a name. T1 is perhaps a more helpful name, and you can see these are the spectra that are included, and those are the ones that are not included. The other tab we want to go to is the series tab, and this is where we set up all the delay times. Now, here for the units, I should emphasize it's important at the moment that you select seconds. So in theory, if you were to select milliseconds, we ought to be able to automatically add that 10 to the minus 3 factor. Turns out to be slightly more complicated to implement that than we had hoped. So for the moment, please make sure you're always entering everything in seconds. And then you can see in the spectrum names, I've always included all the delay times, so we can just add those in manually. You will notice that some of them are actually repeated, so that's just to give us a bit of a sense of the error. And then if you wish, you can order these small to large, and I've got them all in order. So that's all looking okay. And then I do exactly the same for the T2 data, select them all, make spectrum group from selected, give it a name, and then go to my series, select seconds, and then here we've got a dash always, so this is 3.6 milliseconds. I don't think that would be in order. Now for the heteronuclear NOE data, again, we're going to group this. I'll show you an alternative way to do that if you prefer. So in this spectrum groups section, you can also go to new spectrum group and double click that. And then you would want to drag over the spectra of your choice. So that's another way to create your spectrum group. Call it Het NOE. And now, obviously, we haven't got a delay time as such. What we're doing at the moment is we're just giving it this AU, stands for arbitrary units. And then I think this one should be 0, 1, and that needs to be 0. Okay, so I think what we might do in future is that we have it with keywords, with strings, so you type in saturated or unsaturated. We may make a few more changes, but at the moment this is how we're distinguishing the two heteronuclear NOE spectra, the one that's saturated and one that's unsaturated. The other thing that's worth doing at this point is making sure that your spectra overlay nicely. So I've got here, this is obviously my assigned reference spectrum, and that's got all the peaks, and I'm going to want to transfer all these peaks and those assignments onto the peaks in all of these other spectra. So I need to make sure that they're all overlaid nicely. So you can see here that actually looks like those overlay well. Let's try one of the T2 spectra. That's the same. So obviously this is nice tutorial data. We've made sure it all works nicely. But if you find that for some reason yours are slightly off, then just make sure that you correct your referencing. There are various different ways you can do that to make sure that they all line up nicely. And now finally, I'm just going to show you one other way in which you could import all of your data, and that is using an Excel file. So in this tutorial data that we provide, there's this relaxlookup.xls. You can see here we've entered all the data about our spectra into this Excel file. We've specified which spectrum group we're going to want to put those into. This is the path to the spectrum data file. So it's relative to where this Excel file is placed in your file structure. This is just the name that you want to give your spectrum. Here we've now got our delay time, unit. The nice thing about this is that you can specify the colors in advance. So at the moment, if I were to drag in all of my T1 spectra, they're kind of, you can see they're kind of random colors. You can specify the colors in advance here. Obviously, it's up to you whether you prefer. At some point, you're going to have to type in your delay times into the computer. It's up to you whether you prefer typing it into Excel or whether you prefer typing it into our program directly, as I've just done. But obviously, if you do a lot of dynamics experiments, you may find it nice to work with these Excel tables and just use search and replace to make changes. So the way I would then import this, let's just start again with a fresh project. So I don't want to save that. So I'd start with my little project with my assigned HSQC. And then I just go to my spectra, take this Excel file, drag it here onto the sidebar, and you can see it's put in all of those spectra. It's created the spectrum groups. And if I double click, you can see it's entered all of these times. And if I drag these in, you can see I've got nice colors as well. If you want to check your spectra individually, quite a nice little trick is that you can use the tab button. If you click tab twice, then it just moves through each of the spectra on that spectrum display one after another. Tab A switches on all of them, tab Z switches all of them off. So that's quite a nice way, just if you want to have a quick check of all of the spectra that you've got there. Okay, so let's have a go now at actually looking at our T1 and our T2 data. So we're going to go to the view spectrum and go to this relaxation analysis, or you can just type RA as the shortcut. You'll see it says beta in brackets. That's because we are still doing quite a lot of work on this and making quite a few changes. So I think the sort of fundamentals of how it works is going to stay the same, but we keep having new ideas for how to make it all a bit more user-friendly and a bit more streamlined and a bit more bit easier for people. So you may find that, you know, some of these buttons change their name slightly. So this setup button might also become a create button, but the basics will stay the same. And we hope then that sort of towards the end of the year or early next year, we can take the beta bit away. Okay, so this is the module that's been opened, and I've now clicked here on this gear button to open the setup, and that's where we're going to set everything up. So I've going to start with my T1 data. So obviously for experiment, I need to select T1. That will automatically fill in some of these boxes. It will also make a few changes in some of these other tabs. And so it's automatically, in this case, recognized that I've got a spectrum group called T1, so it's selected that. Obviously, if you've called it My Amazing T1 Data, it probably didn't recognize it, and you may have to select it from the drop-down menu. The next thing we have to specify is the so-called input collection. Now, collections, you can see here on the sidebar, we've got a little tab called collections. That's basically just the way in which you can group lots of different objects in our program. And what we want to do is group all of our peaks, because obviously here, what we're wanting to do is copy this peak from the assigned spectrum into all of these T1 spectra, and then we want to fit all of these together, and we want to fit all of those together. So each of these sort of groups of peaks, we're going to now bundle and group into a collection. So the way we do that is to click on setup to set up our collection. And so obviously we want to deal with the T1 data, so I've got that spectrum group selected. This is now the peak list from which I want to copy the peaks and copy the peak assignments. So you can see in my peak list, that's the only one that isn't actually the T1, T2 NOE data. Then we give our collection a name. I actually prefer to call it peaks. And then we just stick with this default option to copy the peaks in place. So it'll copy them in exactly the same position. It won't alter them. It won't try and fit them to a new place. But we are going to keep this refit peaks at position selected. So that basically once it's copied all of the peaks into these T1 spectra, at that same position, it's then going to fit them to get the correct height and that kind of thing. Now, Gary's raised his hand.
Yeah, I was just going to say, you may be tempted to put follow peaks on, but it actually gives you considerably worse data fitting if your data is correctly measured. If you find that your peaks are moving, it most probably means there's something wrong with your data measurement, and most probably in terms of temperature control.
Yeah, So the follow peaks is actually something we use more for if you're doing titrations or something like that. So that's why, yeah, you would expect for the dynamics data to be able to copy them in place. And then therefore have them all in the same place and refit them in the same place. So we'll just click OK.
So what we're doing here is essentially determining proper intensities for the peaks that we have first copied over. That's the fitting. We're not doing yet a T1 or T2 fitting. That's a second fitting, which will come later.
Okay, so let's just have a quick look here under collections. If we open this up, you will see that for each residue, you've got a collection. And if I right click on here, you can see what's inside it. So here for lysine 18, you can see we've got all of these peaks from all these different spectra. That's what's been collected together there. And we've got that for every residue. And then right at the end, we've got an additional collection, which has collected together all of those other collections inside it, because that's all of what's part of the T1 data. So that's what's going on there. Okay, so that collection has now been selected here, and then we're now going to basically extract all the information from all of these peaks and put them into a table, which we can then use as our input data when we want to do our fitting and get our relaxation rates out. So you can just use that name or a different one. All we need to do, we've selected all the correct options here, is to say create. Take a few moments, here we go, and that's been selected for us. And so then the next thing to do is to actually do the fitting. As I mentioned before, when we selected T1, this has actually already been set. So under calculation, we're not really doing a calculation, so that's just blank. We are doing a fitting, doing this one phase decay. So if I hover over that, you can see a description. So you can see the equations, just an amplitude, then e to the minus rate, oops, times x. So that's the equation that we're fitting. I think if you did this one, that's how you get relaxation times rather than this one will give you rates. We're just using the standard optimizer method, but there are many different ones. If you're into this kind of thing, you can choose other ones. Okay, so that's all selected. So we click on fit and automatically selects this results table and go to appearance. So by default, this is a scatter graph, and I'm going to change it to a bar graph. And we also need to check what's being plotted. So we've got the residue code on the x-axis, but here we've got the amplitude. We actually want to plot the rate. So that's looking much more like what I would expect for a T1 plot. Okay, so we've got at the top, this is our results table. If I click on one of these, and you can see on the right-hand side, I've got this little plot, which shows all the different data points. They're coloured in the same way as the spectra are coloured. And I've got the fitting line, so I can see whether that looks like a decent fit. Here I've got a bar chart of my results, and they're all linked with one another. So when I click on here, I'm automatically going to that peak in the spectrum. This bit on bar chart is being highlighted, and similarly I could say, oh, look at this, that looks interesting, that's a bit of a low value. I can click on that and I can see, okay, this is glycine 55. Well, that's something we might expect, that would have a be quite mobile. All right. So for the T2 data, what we do end up doing is pretty much exactly the same. So I'll take you through this a little bit faster. Click on T2, select our T2 spectrum group. We need to set up our input collection. So it's the T2 spectrum group, starting with the peaks on my GB1 HSQC. Then I'm going to call that T2 peaks, copy them in place. So just go with the default options. And I create my T2 input data table. Here I just need to make sure that I remove the T1 input data table. And then the fitting is exactly the same. So I click on fit. And here I've got my T2 data, and I can start going through that and having a look. Obviously, at the moment, I've got my T1 spectra here. I could just drag in my T2 spectra and compare that. So next up is the heteronuclear NOE. It's pretty much the same process again. So we start by selecting experiment name het NOE. We're selecting the het NOE spectrum group. We set up our input collection again, all using the same process as before. Obviously it's much quicker because we've only got 2 spectra this time. Then we create our input data table, remove the T2 table, and then we can do our fit. I'll just show you what's actually happened when we selected het NOE here as the experiment name. Then in the calculation tab, this moved on to het NOE, and you can see here it's just a straightforward calculation of the ratio of the intensities from the 2 spectra. You can see how errors are propagated, and the fitting this time is blank because we're not actually doing a fitting, we're just doing that straightforward calculation for the heteronuclear NOE. So we can now click on fit, and calculation is already done. And here are our results. And again, we can move around the spectra and the table. Obviously, you won't get anything in this fitting graph because no fitting has been made. So we now come to our combined data analyses. So looking at the R2 over R1 ratio and the reduced spectral density mapping. So once again, we'll go to the settings panel of our relaxation analysis module, and this time we can skip the top few sections and just go directly to input data tables. So these are obviously the tables that we're going to need for our calculation. So for the R2 over R1 calculation, we don't need the heteronuclear NOE input data table, but we do need the results from our T1 calculation and the results from the T2 calculation. Let's give the results table a good name, R2, R1. And then we need to make sure here in the calculation tab that we're selecting R2 over R1 ratio. And again, if you hover over here, you can see how the calculation is done. And the fitting again remains blank. So now we can fit this. And here are our results, which you can view, and the table to go with it. And again, obviously this fitting graph will stay empty. To do the reduced spectral density mapping, we will need the heteronuclear NOE data as well as the T1 and T2 data. So we're going to select the heteronuclear NOE results table, add that in here, and then reduce spectral density mapping. And on the calculation tab, that's what we need to select, reduce spectral density mapping. Fitting again can stay blank. So let's click on fit. It's now worth going to the appearance tab. Because the values are really small, there's some kind of bug which means that the bar charts don't really work very well, so it's better at this point to switch to the scatter plot. Hopefully the auto zoom, that's right, will give us a nice graph here. So you can see now the values for J is 0, and you can see we've also got J omega X and J omega H. Which you can just select here to be displayed on the x-axis. So that's all of the calculations for the reduced spectral density mapping. Obviously all of the raw data is always in all of these data tables, which are here in this data tables section of your project. So if you ever wanted to refer to this, you can always open these, but it's up to you as to whether you find this helpful or not. We're now going to have a look at how you can export some of your data. So obviously any table in Analysis, you can always right click on it and you can select to export either all of the data that's there. So when it says all columns, it'll be literally all of them. So if you right click here on column settings, you will find that very often there are certain columns which have been hidden and are not being shown. Obviously you can always select to view more of these. So if you select on export all columns, and it will export literally everything. Export visible table will just export what is currently visible. So if you've applied any filters, for instance, then it's only the things that are remaining in here after you've done the filtering that will be exported. You can export these graphs as well. Again, just right click and then export. I think there is a bug in the export to SVG at the moment, but you can certainly create a PNG, TIFF or JPEG image from these. But then we've also got a macro which will create some nice PDF files for you. So if you go to the macro menu and then run CCPN macros, and then at the bottom in this relaxation section, you've got this relaxation plots pop-up macro. So you can see here, we need to select a data table. So this takes as the input the reduced spectral density mapping data. So that's sort of got all of the data in it. The plots that will be generated will go into this path. By default, it goes into your project in the data folder. There's a plots subfolder. We've pre-filled this obviously with the GB1 data. So here you can enter the one letter code for the sequence of your protein, and then also the secondary structure if you want to have a little ribbon diagram at the bottom of your your plots. And then we'll just leave all of these selected for the moment, and I'll show you what all of these are. So we'll just click on generate. So these plots, let's try and find them in our folder. So this is the project I'm in. So in the data folder under plots, here we go. So this first one is the relaxation rates, and you can see here it's plotted R1, R2 and the heteronuclear NOE, and because we've entered the sequence and the secondary structure, we've got those plotted along here at the bottom as well. Then we've got some plots for looking at the anisotropy. So here we're looking at R2 over R1 and R1 times R2, and trying to get a sense of how the protein is tumbling. Then we've got the reduced spectral density maps. So here we've got the spectral densities plotted again with a secondary structure, and then here you can see some of these other plots that Gerten was showing in his talk, plotting spectral densities against each other and comparing it to sort of idealized curves. And then finally there's also this T1, T2 contour scatter plot. This was part of version 2, and so we decided to include that here as well. That just shows here T1 versus T2, but superimposed you can see in blue is the rotational correlation time and then the order parameter. So you can see it's clustering here at around between 4 and 4.5. So I think we're expecting a correlation time of about 4.3, so that fits, and an order parameter of around 0.8. So that's where most of the points are clustering. So because I had selected interactive plots, in addition to these PDFs, on my other screen, there's also some interactive plots that have opened up. These are generated by Matplotlib, and so those of you who are familiar with Matplotlib perhaps know what to do here, but it's just a chance for you to perhaps change some of the parameters before you save this. So if we click on this one, you can change the spacings between some of the different graphs. This icon here lets you select each subgraph separately, and then you can change make changes to the title, the scaling, and all of that kind of thing. So you can do that, and then when you save, you can save to lots of different format types. So that brings the practical side to an end. We hope that's given you a nice overview of everything, and do get in touch if you have any questions.